sorry, I think there was setting problem. Okay, so let me start again. Good morning, everyone, and then good night, and then good evening too. Let's see, this Friday, the first session will be start with the Collider plenary session. So two talk from LHC and then future Collider. So the first talk will be given by Professor Todd Adams from Florida State University. The title of talk is Search for Beyond Standard Model Physics at the LHC. Let's welcome Professor Adams.
All right, thank you very much. Okay, let me share my screen, my slides, and we will get started here. All right, does everything look good?
Yes.
I'm going to change my laser pointer. Sorry, I thought it would remember to green so that it will show up. Okay, so thank you very much. So today I will talk about searches for the Beyond Standard Model Physics, the LHC. I'm going to talk about results from the ATLAS, CMS, and LHCb experiments primarily. So the LHC has an incredibly diverse physics program. Many searches have been carried out looking in the obvious places for new physics, looking in the less obvious places for new physics. I'm only going to have time to go over some of the results, just a small fraction of them, some of the newer results. There are other talks that have already been given here at this meeting covering some of the topics that fall into this category. I list some of them here. The talk following this will also have some new physics searches involving the Higgs boson. So unfortunately, because of the vast number of results, we're not going to have time to go very deep into it, but we're going to get an overview of it. So hang on to your seats and we'll have a quick tour of there. So I want to start off and set the stage on the strategies. So because there are many different approaches that can be used to look for new physics. One way to divide it up is searches can be motivated either based on theory, because there's a beautiful theory that somebody likes and wants to say, for example, prove that Susie is out there, supersymmetry exists. And they like the beauty of that theory. And so that motivates how they approach searching for new physics. Other people will look at a final state and say, well, there's not much chance of observing standard model physics in this final state. If we look in there, and we find something, an excess of events, then we've got a signature of new physics, and it's not necessarily motivated by specifics of what might be found, but just finding something. And there's a whole spectrum in between of people who are motivated partially by theory and partially by final state. And we'll see a little bit of that today. You can also categorize it as the searches by direct versus indirect. So lots and lots of particles in our field have been found by bump hunting, looking for a excess of events at a specific mass in some specific decay mode. One of the more recent ones is the Higgs boson. If you look at the diphoton invariant mass, you see a bump at the Higgs boson. It's a beautiful result and just clear evidence of something new going on there. Event counting is similar, but not looking for a specific bump, but looking for an excess of events. So knowing how many events you should have and then comparing it to what you observe, and an excess or even a deficit of events can point to new physics. Precision measurements fall more into the indirect category, where you measure a value that you know, some parameter you know the value of, and if you measure it, find out that there's a disagreement, it points to new physics, which may or may not be obvious what that new physics is directly from that. And deviations in kinematics is another one. There's lots of different ways to look at it. This is just a few of them. Another important thing in the strategies can be, how do you predict how many events you expect to observe, or the way they should look, or the parameter you're measuring. Simulation can be used, or data-driven predictions are often used, and combinations of these can be done. I also wanted to mention that machine learning is becoming a important part of many searches, adding power to our searches and allowing us to dig deeper into the data than we had before. We're going to see some of these examples through this talk, but I wanted to just leave you with the idea that the main goal of searches is the evidence of new physics. And I'm a strong believer that the greatest improvement in our knowledge of the universe will come from discovering something new and giving us guidance on what models are correct or not correct. And so we're going to learn the most by finding something new. So we want to look high and wide, and that's what we've been doing at the LHC. So I'm going to start off with a result from LHCb on lepton number violation. Here we're looking at charged B mesons decaying into a kaon and a mu plus mu minus, or an E plus E minus pair. And they show you in the upper right the standard model diagram of this process. And the branching ratio for this is small, 10 to the minus 6, but that's on the level of the sensitivity of the LHC now. But what I really like about this, come to appreciate this search, is that the standard model would predict that the branching ratio to electrons should be the same as to muons. And this is as long as you're above the thresholds that make kinematic difference between electrons and muons, and that's pretty easy to do at the LHC. So you expect that if you measured the number of decays to muon pairs or electron pairs and took that ratio, you'd get a value of 1. But new physics may not follow that. So I'll give you an example on the right of a new physics process involving a leptoquark, where the leptoquark may have couplings to a specific flavor of leptons, and so it may modify and not have an equal amount. So LHCb measures the ratio of these, but actually measures a ratio of ratios. And as a young scientist, I was taught by one of my advisors that ratios are wonderful things, because a lot of the things that you don't know, a lot of the uncertainties you have, cancel out with ratios. And so you can advance your knowledge without having to know some of the details as well by using a ratio. So here we're going to measure the branching fraction to this k mu plus mu minus divided by the branching ratio of the B to a j psi k, where the j psi decays to a mu plus mu minus. We're going to call that resonant decay, and non-resonant the one where it doesn't go through the j psi. And we're going to take that ratio and divide it by the ratio for electrons, and lots of things are going to cancel out here and reduce our uncertainties. So here we're going to replace the branching ratio that's being measured by number of events corrected for reconstruction efficiency, and use that to do this. So, and important to note that this result uses a larger data set than the previous measurement done by LHCb. So here are the invariant masses of the KEE system. The top plots are for non-resonant, and the bottom ones are for decays through the j psi. And the left plots are E plus E minus, and the right plots are mu plus mu minus. And you see huge peaks down here with the j psi decay modes, 10 to the third on the axis, note that, while much smaller in the non-resonant decay. So we still have sensitivity to it. We're seeing the B meson decaying this way, but at a much smaller rate. And we're going to use effectively divide the top row by the bottom row, and then take the ratio of the right column to the left column. So in doing so, LHCb determines a ratio of 0.846. The first set of uncertainties are statistical, and the second set are systematic. And you see graphically the results here on the left. The LHCb measurement is down here. Bell and Bobar are shown here. And you can see that LHCb's result is clearly not consistent with 1 at the 1 sigma, and even more than that level. So we can quantify that by looking at the right plot, which is the negative log likelihood, and the most probable value is our 0.846. The dark blue area shows a 3 sigma range on the high side, and the light blue goes out to 5 sigma. What we find is LHCb's measurement is a 3.1 sigma deviation from the standard model. So this is significant. It's not a 5 sigma result, but it's more than the 3 sigma result. So that points to some possible new physics, not necessarily telling you the nature of it, but it gives something interesting to guide us going forward. I wanted to show Atlas has recently taken some of their results that have already been done, which I won't go through the details, but they've combined multiple searches for leptoquarks, and this is pair production of scalar leptoquarks, and shown if we look for different states here, how do they go together and what masses and branching fractions are excluded by their previous results. And so the top 2 plots are for up type leptoquarks, and the lower ones are for down type. All of these involve decays to 3rd generation quarks, but the left column is to 3rd generation leptons, and the right column is to 1st and 2nd generation leptons. So this shows the areas that have been explored and excluded at Atlas for leptoquarks. Doesn't necessarily tell us how that relates to the previous measurement, but it's a nice summary and a way to put together multiple results that was recently done by Atlas. Moving on to other analyses, Atlas has done a monojet analysis, and monojet is a classic analysis at a collider experiment. It's considered a golden channel because there's so many different things you can explore here, and it's generally fairly straightforward. So the idea is you look at events with at least one high PT jet. You require there to be a large missing transverse momentum. We're going to use MET as an abbreviation for that some of the time. We're going to require that to be greater than 200 GeV, and we're going to reject events with leptons in there. And there's a lot of different possibilities that can create events that look like this. So you're looking for something recoiling against something else you don't observe. And we're going to observe the jet, but we're not going to observe some new physics. So examples include such things as dark matter, axion-like particles, extra dimensions, supersymmetry, and a dark energy inspired model here can be explored with this channel where you get a jet. So for example, in this diagram, the jet comes from this gluon radiated off one of the quarks, and you don't observe what is created there. So it's a very powerful way to explore things that the detector can't see. The data is shown here for one of the signal regions that is for the signal regions is used here. Data are the black points. The filled histograms are the prediction, and the ratio of the data compared to the prediction is shown in the bottom panel down here. And you see that there's good agreement between what we observe and what we're looking for. Signal is shown as a dashed plot in here. So those are some general trends that we'll look at in many of the plots, those types of coloring and use of histograms there. So from that, we can set limits on all these different models. I'm not going to have the chance to go through all the limits that are set in all of these models. So I just want to show you the wide variety of things that can be done. This is an example where we look at one state and can then apply it in a wide range of topics. So CMS has done a similar search, which is entitled Looking for New Particles and Events with Energetic Jets. And here they require large missing transverse momentum, greater than 250 GeV, recoiling against something. And now 2 things are considered in this analysis. One is a mono V, where V stands for vector boson. And you're looking for a vector boson recoiling against something. And we're assuming that that recoil gives a significant boost to the vector boson such that its decay products are close together. And here we're looking at then at decaying to hadrons, and those 2 hadron, the jets from those 2 hadrons being close together enough that we find it by looking for a wide high PT jet. And so that's a mono V channel. And then there's a monojet channel. We divide the data into either of these 2 possibilities, whether we find the vector boson decay or not. If we don't, then it's called a monojet. We show you what the PT miss it looks like for the monojet on the left and the mono V on the right. Again, comparisons to the ratio down here. The analysis does a simultaneous fit to the signal region and control regions using data-driven backgrounds here, and fits the different samples to get the best description of the data. And from that, unfortunately, again, not finding evidence of new physics here, you can again explore multiple models here shown with SUSY in a number of different channels, extra dimensions, leptoquarks, and Higgs decaying to invisible particles are explored here. Atlas has done a search looking for SUSY, but with R parity violation. And here the R parity violation is baryon number violating. Often the R parity violation searches involve lepton number violation and look for lots of leptons. This one uses the baryon number and therefore looks for lots of jets. So the analysis requires there to be at least one lepton in the event, but many jets, anywhere from 8 to 15 jets. It's done with different thresholds. So you run the analysis with one jet threshold, and then you run it again with another jet threshold, giving you multiple signal samples, and also divided up by events that have 0 BTAG jets and those that have more than 2, so 3 or more BTAG jets. And here you skip over the region where you have so much top background by doing that. Then divide the data into 2 categories. Ones where you have 2 leptons with the same charge, and then all the other events fall into the other category. And recently a new neural network has been added to try to discriminate the top background. So in fact, you can see from this diagram here, the number of BTAG jets is here, and green is top production. You still have a lot of it, so you want to try to discriminate against it, and a new neural network has been designed to do that for events where there's at least 1 BTAG in there. The analysis uses a data-driven technique, and to show you here the number of BTAGs and the number of BTAGs where the BTAG bin is divided into neural network bins that are, when you get higher than 1 BTAG, and they're divided such that there should be equal amount of signal in each bin. And you see the dashed histogram is fairly flat in here on the neural network bin, while the signal is falling. So it gives you additional power by adding this neural network into the analysis. Still haven't found evidence of new physics here, but a key part of this is the first sensitivity to SUSY electroweak production using R parity violation with full hadronic decays that's happened since LEP. So a new window has opened into different physics at the LHC with an analysis of this type. So that's exciting to see. CMS has done a SUSY search in trileptons, another classic signature. Here we're looking at production of charginos and neutralinos, and there are many processes that are considered here. And in doing this analysis, the data is divided up into 12 categories, which are shown in this table on the right-hand side, starting with 2 light leptons, where light is an electron or a muon, that have the same charge. And then going into 3 leptons, sometimes determining whether there are opposite sign, same flavor pairs in there, or including in hadronic decaying tals. So you can see the 12 channels that are considered here. Different models will contribute different amounts to the different categories. A neural network is used to help discriminate signal from background, and simultaneous fits are done to various signal regions to extract how it applies to a given model. A comparison of data in one of the signal regions, here, the one with the first one, 2 light leptons with same charge, you see the data and the expected backgrounds are again in fairly good agreement. So from that, you can set limits on lots of SUSY parameters, the masses involved, depending on the production mechanisms, there's a lot that can be explored with this one trilepton analysis. Again, another reason why it's a classic signature to look at. Atlas has done a search for production of neutralinos and or charginos in fully hadronic decays. And here you have an advantage. The leptons are nice clean signatures, but the hadrons have a much higher branching fractions. So show you some diagrams here on the right, where if you have decays to WZs or Higgses, then the decay modes to hadrons are much larger than to leptons. And so you get more events out of the same luminosity by looking for the hadrons. The key then is just to be able to dig these events out of all the QCD jets that are there. So one of the tricks that's used here is to use boosted boson decays, again, looking for that boson production where the decay products are close enough together so you get a large radius jet. They apply boson tagging to identify that that's what happened here, and divide the data into two categories, one where there are just 4 jets, and another to separate out where 2 of the jets are B tagged, so that you have that one boson decaying to Bs and the other to other quarks here. So it's divided up there. Use simulation to estimate the background in there, and then do 3 different fits to the signal region and control region. So the first fit does a background only fit. So you look at the control regions and just see how much you have to adjust it to describe the data compared to what you expect. And the background does a good job of describing the data already. The second fit is a discovery fit where one signal region is considered at a time. And you allow then to see how much signal might appear in that region, giving you an ability to measure or set limits on the number of events, therefore the cross section that might produce those events for just that one signal region. And then the third is an exclusion fit where you consider multiple signal regions at the same time within a model and see how that affects the ability of that model, the presence of that model. So here's a plot showing the bins are of different signal regions that are considered. The 4Q is the QQQQ, and the 2B, 2 quarks is where you have 2B jets, and different bosons that are involved in the decays. And again, you see reasonably good agreement between the data and the expectation. So that allows us to explore, again, a lot of SUSY space. And you see the areas that are excluded for these. CMS, moving away from SUSY, CMS has done a search for a resonance decaying to a top and a W boson. So here the model is some B star, some new B-like resonance, that if you get to high enough mass, so a mass greater than 700 GeV, the top W becomes the dominant decay mode. So you see these searches begin at 700 GeV and don't look below there. But we're looking for something then in this decay. The top is going to get boosted. So we reconstruct the top decaying to a BQQ as one large jet with substructure. And the W decay, we're looking at the lepton plus neutrino decay mode. Going to divide this data up into 3 categories. A 0B jet allows you to look at the non-top background. The 1B jet is our signal because we only have 1B jet in here. And the 2B jets allows us to control the top background, because the pair production of top or the single production of top will give you 2 B jets in it. So we fit those 2 regions, the 1 and 2 B jets simultaneously, show you what they look like here on the left hand or the right hand side. And again, we're seeing good agreement between the data and the expectation there. So from that, we can set limits on the existence of a B star resonance, considering a left-handed, right-handed, and a vector-like resonance. And you see on the bottom, the mass limits that are around 3 TeV. We're excluding a new resonance decaying to top plus W at on order of 3 TeV, pushing this, it's going to be hard to push that all that much higher with the LHC energy that is available. Moving into a new category of long-lived particles, LHC has done a search for long-lived particles decaying to an electron, a muon, and a neutrino, considering several different production mechanisms, some of them shown here in these diagrams in the upper right. And the idea is that these long-lived particles travel some distance and then decay to this electron, muon, and neutrino. And you reconstruct that by finding that electron and then the muon and finding them from a vertex that is well away from the production point there. The nice thing about this analysis is it is complementary to analyses that can be done by ATLAS and CMS. Because of the design of the LHC experiment, it's going to look for low mass particles and low PT particles. And so we see down here the corrected mass value calculated for the data. This is the black histogram, and the green shaded area is the simulation. And the red shows what a signal looks like for a 7 GeV object with a 10 picosecond lifetime. And then over here we see the reconstructed vertex position, and you see sorry, hanging up on that. You see the reconstructed vertex, and depending on the lifetime, depends on how far out you see there. But there can be clear signals in this analysis, clear evidence of something new when you look at it. A boosted decision tree is used to enhance the searches, and this decision tree, the signal is shown as these colored histograms that are fairly flat in the BDT output, while the background and the data and the simulated background are both peaked at low values. So you can look for an excess at high values of BDT, and not seeing that there allows us to then set limits on the production times branching ratio for different masses and different lifetimes. Show you here for a fixed lifetime in the middle and different masses, and then for different masses as a functional lifetime on the right. CMS has done a search for displaced di-muons. So the reconstruction of a pair of muons that are, again, not from the vertex. You have this uses scouting data, which is an interesting development in the recording of data. It uses a reduced event size. So you only save part of the detector data. In this case, the muon system data and the tracker. And that allows you to set lower thresholds on the data and record more events for the same amount of space. It gives you more throughput. And so the signature is 2 muons from a displaced vertex. We're going to categorize this by the vertex position, 6 different regions. I show you that down here in the bottom right, where you have 3 within the beam pipe and then 3 within the pixel detector. So you're looking for production of something that decays fairly early within the pixel detector, but still away from the production point. And the model is that you have B meson production decaying to a phi and something else, and the phi is the long-lived particle that decays to the two muons. Show you here the reconstructed di-muon mass. This is for the closest bin and vertex. The other way that the data is divided is by the muon PT, below less than 25 GeV or greater than 25 GeV. This is the less than 25 GeV. And you see a lot of data. You see a couple of known resonances of B mesons, or of mesons here. And the signal is shown as these green and red histograms here. So you see from this data, it's going to be very difficult to find the signature in there. You might think of it as hopeless. Note, this is a semi-log plot, or it's a log-log plot, and that's a lot of orders of magnitude there. But when we divide it up into these categories, on the left-hand side, you see the PT less than 25 GeV, and on the right, the PT greater than 25 GeV, and the 6 different vertex position categories in there. And you note that when you get up here into the high PT, now the signal starts to appear significant here, and it might become easy to find a signature in this data. So looking through here, we don't see a new bump arriving, appearing in the data. And that allows us to set limits on the branching fraction of the B to this phi plus other things. Here shown for several different lifetimes. And as a function of the mass of the phi, where we've excluded regions where there are known resonances. So not looking for a bump on top of a bump, and they're just looking for something in the new regions. And you can see there are many orders of magnitude covered in here, from 10 to the minus 6 down to 10 to the minus 10, 10 to the minus 11 on the limits on the branching ratios for these particles. So I'm going to skip over this analysis unless we have time. How are we doing on time? Okay.
So you can have a 3 minute more.
Okay. All right. So I'm skipping this one. I want to do the disappearing tracks and then wrap up. So Atlas has done a search for disappearing tracks. Here you have a charged long-lived particle that travels through the pixel detector and then decays to a neutral long-lived particle and a charged pion. And if the mass difference between the charged long-lived particle and the neutral long-lived particle, here's a diagram with a chargino and a neutralino, if it's small, then the PT of the pion is low and the particle curves and it disappears. So you have hits in the pixel detector and nothing in the strip detector, and that's the signature that you look for. Using data-driven backgrounds for this, you see here the production. If you look at electroweak production, the number of predicted and observed events, and strong production, here are the numbers of events again. Agreement, so you can set limits on the parameters of SUSY here for both the electroweak and the strong production. So just to show you that I've only shown a few of the results. This is a summary plot from CMS of their Exotica results, not including SUSY. And the colored bands show you the excluded mass regions, but you probably can't read it because there's too much information on here, just showing you the range that's there. Atlas has similar plots. I show you their SUSY searches. Again, a wide set of searches that have been accomplished. Just to wrap up, searches continue to be a driving part of the LHC program. We're going to double the data set in run 3. But more important than that, new ideas and analyses are being developed within the collaboration. So some of the ideas and the results that we've talked about today weren't even thought of 5 years ago. And some of them maybe even just within the past couple of years. We're getting inspiration from theory and experiment. And one of the areas that's become hot and exploring things that weren't considered a driver to the LHC program in the beginning are searches for long-lived particles. Showed you some results there. But there are operating, planned, and proposed detectors to enhance LHC's program there. I list some of them here. We heard from some of them during this meeting. So there'll be much more coming from there, from the Atlas CMS and LHC program, and from these many other ideas and experiments that are coming about. And we're going to hear some more new results in our next talk. So I will wrap up there, say thank you, and see if there are questions.
Okay, so thank you, Todd. Do we have any question for Todd Adams?
Well, let me get to the chat. There we go.
Do you have any other question to Todd?
covered a lot in a short period of time.
Yes. And so Todd, you talk about all kind of the PSM physics at the LHC. So the next year, the Learn 3 will be started. And as you pointed out, it's only basically the same size of the data set with respect to the previous data. So do you think is there any particular the physics item we should focus on in Learn 3? I mean,
there are new ideas being developed, particularly on the trigger side of things. People are trying to find ways to record data that we may not have seen. So many of the classic searches are going to be slow to benefit from the new data. Right? So next year's data is not going to be a large addition to there. We still have a lot going on with Run 2, and some of those analyses will move on to start including Run 3 data as they come along. Specific places of major advantages. I work in long-lived particles, so I think that's actually a really interesting thing where we're adding ideas that haven't been looked at before. And that will continue for quite a while, I think.
Okay, actually, since there is no other question, actually, I can ask one more question in detail. So if you look at like page 12.
Okay.
Yeah.
Let me get back to page 12. And let me see if I can move this because I can't see my page numbers right now. Okay. Whoop. All right, page 12.
Maybe it was page 11, I guess.
Okay. Energetic jets.
Okay.
Maybe. Which analyses were you?
Can you go back one more page? Okay, yes, this one. Mm-hmm. So I mean, here you are the plot right hand side. So you are looking for basically the dark matter through the mono vector boson.
Yeah.
So then I'm wondering why the dominant background is the G plus Z. I mean, shouldn't you look? I mean, the dominant one shouldn't be like divergent where one boson goes to the neutrino instead of the G plus Z.
It's in there, but
so here in case of the mono V, yeah. So this V goes to the, so this one goes to the dilepton or it goes to the Z? This boson.
In the red, the Z is going to are you asking about the red part of the histogram or?
Right.
So this red is going to neutrinos. And so the jet is then contributing. You see that is bigger over in the mono jet part and smaller here. Still an important piece of it, but it's even more dominant in the mono jet part of the analysis. Right. So but you pay the price in the WZ and ZZ, where the Z is going to neutrinos. You just have a lower cross section.
Okay. Yes. Okay. Okay. So thank you, Todd. So
could I make a comment?
Yes.
This is actually really interesting what you pointed out, and it's a general phenomenon. As you go to very large PT, as you go to eventually very high energy, it's always the top that turns out to be the most important background. We're not quite there yet in these curves, but it's clearly a trend. This QCD production and then all kinds of crazy things that happen in the final state will dominate. And eventually, this is going to be the problem for many kinds of searches that you would like to improve.
Yes, many of us have gone through a transition where the top weren't even sure it was around. Just finding it was challenging enough, and now it's like, let's beat it away.
Okay, so let's move to the second talk. So thanks to Todd.
Let me see if I can stop sharing.
Yes.
If I can get the right, it doesn't want to hit the right button here. Hold on. Okay, let me escape out of here. See if I can get out first, and then we'll stop sharing. My apologies for technical challenges.
Yan and Liu, are you there?
Yes, can you hear me?
Okay, yes, good to see you again. So, okay, the second talk is the latest LHC result on the Higgs boson and then multi-boson physics. So this talk will be given by Yan and Liu from University of Science and then Technology of China. Okay, let's welcome Professor Liu.
Can you see my slides in full screen?
Yes, yes. Go ahead.
Good morning, good afternoon, good evening, everybody. This is my pleasure to talk about the recent results on Higgs boson and the multi-boson. Given this topic, I have to make a selection. So I will talk about the mass measurement and search for the rare decays and the differential and the Higgs searches and self-coupling measurements. Then I will highlight a few searches for new fix with the Higgs particle. In the multi-boson part, I will talk about the boson scattering and the triboson production. So I apologize if your favorite topics are not covered today. In this case, you can look them up from these two lists. So the Higgs boson is the core of the standard model, and it has a special role. It's the only scalar particle in the model, and once the mass is known, we know very well the production cross-sections and know very well how it decays. So previously, we have a combination of the mass measurements shown here. You can see the mass is already measured to a great precision. Recently, Atlas updated the Higgs-4 lepton mass measurement with the 4 round 2 statistics. You can see that from the single channel, the precision is already comparable with the previous combination. So this is an overview of the couplings. It's impressive to see that the linear correlations for the coupling or couplings square root of the couplings with the particle masses. So now I will switch to the few searches and the evidences of some rare decays. So CMS recently has established the evidence of the di-muon decay with a significance of 3 sigma observed. The expected significance is slightly lower. So here is the di-muon mass spectrum. The significance in others is still at 2 sigma, and this has been searched for in different categories. And shown here is the di-muon mass system spectrum. The CC channel is very difficult to spot, and the major challenge is from the identification of the C jets. Shown here is the efficiencies for the C tiger for light flavor, P jets, and C flavor, CT plot. The working point is optimized for the VHCC observation. So the analysis includes both resolved and merged topologies and arrived at an upper limit of 70 times standard model at 90%, 95% confidence level. And Atlas also searched for this decay, and the analysis fits simultaneously for the 3 parameters. The signal strength of the CC is consistent with 0 yet. And here is the upper limit 26 times standard model in the cross-section, in the branching ratio. This limit is translated to the constraint on the Higgs-C coupling shown in this plot. And the best fit value is, of course, 0, given this 0 observation. Now, recently, Atlas has established the evidence for the 3-body decay of L gamma. So this analysis includes both the on-shear and off-shear contribution. So it's separated by the event mass of the dilepton system. So for the virtual, the official part, the significance is 3 sigma, and for the onshare part selected by the dipole mass and the evidence, the significance is 2 sigma. So on the CMS side, the research has been carried out with partial round-trip data set, and the current status is an upper limit of 4 times standard model, and the offshore and onshore pieces are separated by the event mass of 50 GeV. So I would now switch to the decay modes with more statistics, and with these, the differential measurements are possible. So I would like to start with the Higgs to WW. With it, I would introduce the simplified template cross-section framework. So the idea is that using the production mode and the kinematics of the Higgs boson and the jets that are produced in association with the Higgs boson to split the phase space to different bins. So this is like a measurement of 11 bin cross-sections with the designed categories. We say the signal regions. So shown here are the measured 11 cross-sections. You can see that in all cases, the ratio to standard model is compatible with 1. While we check the GGF and VBF two combined cross-sections, this is the standard model value and the 1 sigma theoretical band, and here are the 1 sigma band and 2 sigma band from the data. You can see good compatibility of the measurement and the theory. So one way to use this information is to use all these measured cross-sections to constrain this as the EFT. So here, shown here are the inputs used in this constraint. So some of the modes are already updated to full round-trip statistics. Some are with partial statistics. And the parameterization goes like the measured cross-section is a sum of the standard model contribution and the beyond standard model contribution and their interferences. Taking the dimension 6 operators, the interference terms are linear in terms of the coefficients, and the beyond standard model piece is goes like quadratic terms of the coefficients. To normalize the cross-section with standard model high order prediction, you get to the ratios. And if we consider also the decays of the final states and factorize the enhanced or the modified basis ratio to the standard model prediction, all these ratios can be parameterized either with linear or quadratic terms of the Wilson coefficients. So in the fit, we fit both the cases with or without the quadratic terms. So to treat the correlations of the different parameters, the Washoe basis is rotated. So the idea is to diagonalize the expected covariance matrix to derive the combination of different coefficients to form the fit parameters. Shown here are the illustrations of the combinations of the coefficients to form the fit parameters. Shown here are the results. So these are the observed fitted results in 1 sigma and 2 sigma range for the linear and linear plus quadratic terms. And these are the expected fitted results. You can see that sometimes the quadratic terms introduce big differences, which tells us that the dimension 8 operators can have also important impacts. So now the same machinery is used to combine the standard model WW measurement and Higgs to WW. So the input to the fit is the 11 bins of the unfolded lepton PT, the leading lepton PT of these WW events. Here are the fitted results. You can see that some of the parameters are greatly constrained by the data. Some on the others, the limits are still very loose. Now I come to the Higgs to tau. So CMS has updated the measurement with the tau to the differential cross-sections are measured as a function of the Higgs PT jet multiplicity as well as the leading lepton and the 18 jet PT. you can see everywhere there is good agreement between the data and the prediction. Higgs BP, both ATLAS and CMS has established the observation of the BP decay mode. Recently, ATLAS has observed the Z-Higgs production exclusively at beyond 5 sigma. The VPF has an evidence of 3 sigma. The recent developments include the search for the decay mode with boosted topology, and this has a significance of 2 sigma. And the event yield in different beams are always compatible with the standard model. This is the search for inclusive BP production in boosted topology. The data is dominated by the multi-jet background. After subtracting the multi-jet from distribution, we can see clearly the peak from the WZ boson and the top quark. After subtracting them, the left is compatible with 0. So with this, we constrain the signal yield in different PD beams of the Higgs boson. The CMS has also an update of Higgs BP measurement with full round statistics. Apart from the increased statistics, the identification of the B-jet inside the inside of the merged jet is also improved using the deeper machine learning technique. You can see from the same efficiency, the rejection of the QCD background has increased a lot. And interestingly, in the high PT beam, there's a local excess of 2.6 sigma, and the global significance of this excess is less than 2 sigma, and the significance of the boosted Higgs to BP is still at 2.5 sigma. And here the event yield in different production modes. Combination with the previous resolved analysis, of course, the BP decay mode is observed in CMS as well. Now this is the simulated template cross-section of the Higgs gamma gamma in ATLAS. So again, the observable phase space is split to 27 beams, and these are measured with 44 signal regions. The measured cross sections are compatible with the standard model prediction. Shown here are all these measured cross sections in the 27 beams. Interestingly, for the first time, we are able to constrain the T-Higgs production. The upper limit is at 8 times standard model prediction. So these are the for different production mode, the yield is compatible with standard model. This is the result from CMS. So the similar observation in all of the beams, the measured cross sections are compatible with the standard model. Now the Higgs to 4 lepton in CMS has been updated to full round 2 data sets, and these are the measured cross section in all these beams. Everywhere you see good agreement between prediction and data. So CMS used this measurement to extensively study the enormous couplings. So in the most general way, the Higgs to fermion amplitude can be parameterized with the contribution of CP even and CP odd contributions. And this is a general parameterization of the Higgs boson amplitude. So these are the coefficients. If you consider the gauge symmetry, of course, these terms are not independent. These are the correlations. I will just pick one of the simplest constraint from this Higgs to fermion coupling. So this is a negative scan of the production cross-section fraction for the CP odd contribution. You can see the best fit is 0, as expected from the standard model, and you can look up the 1 sigma and 2 sigma bands from these negative curves. So from ATLAS, so they measured the cross sections in different decay modes of the 4 lepton, and as a function of the Higgs PT are compared with the theory predictions. You see agreement everywhere. So ATLAS also used this measurement to constrain the couplings. So one approach is to use the PT of the 4 lepton system to constrain the Yukawa coupling of the PC. Taking only the shape information, you get these contours. If you include the theoretical cross sections, this contour, the limits include a little. Once you also consider both the shape and the modification of the normal coupling in the width and branch ratios, the constraint becomes much stronger. So on the other, with another approach, using the so-called shorter observables. So all these interactions are parameterized with the contact interactions. So these are the parameterized couplings. So you can see the constraint on those parameters with the 4 lepton data. Now I will switch to the searches for di-Higgs production. So in the standard model, the di-Higgs production, it gives us access to the self-coupling of the Higgs boson, as well as the coupling of VVHH required 2CV coupling from the VVHH vertex. The cross sections are very small, so we have to combine all the decay modes. So this is from the previous combination in CMS. So the observed limit is 22 times the standard model. And similar situation in Atlas, they combining all these decay modes. Atlas has arrived the upper limit of about 7 times standard model, and this measurement is used to constrain the self-coupling of the lambda. Now, recent updates of this analysis, so CMS has updated with 4 longitudinal data set for the gamma BP, and this channel alone has arrived at the upper limit of 7 times standard model, which is already stronger than the previous combination. And these are, from these curves, you can look up the constraints on the coupling, self-coupling, and the C2V coupling. So same observation in Atlas, we updated the search with the 4 longitudinal data set, and this channel alone exclude the cross-section beyond the 4 times standard model already, which is much stronger than previous combination. This is the result from the 4B analysis. For GGF, it goes, the upper limit is about 4 times standard model from CMS. And in Atlas, there's a new analysis of WWPB updated to 4 round 2. And the upper limit of this cross-section is 40 times standard model. If you compare it with the previous analysis, this has been greatly improved due to the usage of the deep neural net classifier to extract the signal. Now I'll talk about a few searches using the Higgs decays. So in the standard model, the Higgs decay into neutrinos has a very small branch ratio. So this decay mode has a sensitivity to physics beyond standard model. Particularly, a lot of the dark matter models use the Higgs as a portal for the connection between the standard model world and the dark side. And previously we have a combination of the Higgs to invisible cap branch ratio with a partial data set, and this is the upper limit, about 20%. And this is interpreted as the cross-section of WIMP nuclear interaction. So this interpretation is of course model dependent, but in the low mass range of the WIMP, the limits are already stronger than the dedicated dark matter experiments. So Atlas CMS has recently updated the 2 searches for invisible decay with mono Z and mono Z final state. So these are the derived upper limit to the branch ratios. So so many models predict non-lived particles. So one benchmark model is the so-called minimal scalar extension. So you have a new scalar which couples to the Higgs boson using this portal interaction parameterization. So this can predict either pseudo-scalar bosons that have a long lifetime. So they decay after some time of flight to B quarks or other quarks. So these are the upper limit of this branching ratio from Atlas and CMS. For Atlas, we use the 4P final state, and CMS searched for the 4-jet final state. So this is my conclusion for the part 1. So we have studied the Higgs boson to extensively and found no surprises. So these measurements are used to constrain the physics beyond standard model in various frameworks, the couplings, EFTs, or UV completed models. Now I will switch to the multi-boson measurements. We know that the longitudinal polarization of the gauge bosons are from the Goldstone bosons of the fixed fields. So the study of the boson interactions give us access to the Higgs field dynamics. So recently, both CMS and Atlas have observed the VBF production of the Z boson. With the statistics, both experiments merged the differential cross-sections of these processes. These are shown here are the differential cross-section function for the jet, the two forward jet mass, and the delta eta pt of the Z candidate, and the delta phi between the two forward jets. You can see everywhere good agreement with the data and the design model prediction. So these measurements are used to validate and tune the Monte Carlo generators, which are important to model this process for searches beyond the standard model. Of course, this was also used to constrain the enormous couplings. So, and both Atlas and CMS observed the VV production in the vector boson scattering. Then the significance from Atlas is beyond 5 sigma, and the observed significance in CMS is 4 sigma. So, so these are the data plotted impedance of the machine learning discriminant variable. So you can see that the signal purity is very high at the last bin in both of the two measurements. CMS has a recent update for the study of the vector boson WW production, looking for the polarized production of the WW. So this is a new result, and in this when they restrict that require one of the W boson is longitudinal polarized, the significance is at 2.3 sigma, and this is measured cross-section of this process. So now I will talk about the observation of the triple boson production. So these are very small processes of very small cross-sections. The CMS searched for this VVV production with the multi-lepton final state. You can see that in the 2-lepton and 3-lepton final states, the production of the WWW is evidenced at the level of 3.3 sigma, and in the beams of 4 leptons and or more, the WWZ becomes evidenced at the level of 3.4 sigma. But combining these observations, the significance of VV production has exceeded 5 sigma. Similar situation in Atlas. So the trap boson production has been searched for in the multi-lepton final state, and these are for the WVZ. The significance is at 3.2 sigma, and the WVV is 4 sigma, and the WW is evidenced at 3.2 sigma. So in all these lepton final states, the measured cross-section are compatible with the standard model. So now I will summarize my talk. So in the Higgs sector, there are new searches for the rare decay modes, the lepton gamma Fibonacci decay and the mu decay is recently evidenced in CMS and Atlas cooperations. And with the high statistical decay modes, the differential cross-sections are measured and are used to constrain the Higgs beyond standard model in the frameworks of coupling modifiers, effective field theory, as well as the UV completed models. The Higgs production are used to probe the self-coupling with the update with 4-round-2 data set. We expect significant progress in this direction. With the Higgs decays, we searched for the dark matter and non-limited particles in the decay product of the Higgs boson. So in the multi-boson sector, the VBF production of the single boson and dibosons are observed. Now the collaborations are starting to look into the polarization of the scatterings, which will be very interesting. Both collaborations are starting to observe the triboson productions. So with more data from the for round 2 sample and round 3, we expect huge significant progress in the near future. So the taking home message is that the standard model works so far, and it will be still tested by the data from ADAMS and Edge and CMS. Thank you.
Okay, so thank you, Janet. Let's see. Do you have any question to Yan and Liu?
Okay, if I can ask a question.
Yes, go ahead, Todd.
I don't remember the slide, but maybe a third of the way through the talk, you were showing a Higgs result with vector boson fusion at the 3 sigma level, if I remember correctly.
Yeah, I think it's the BP mode.
My question was, yeah, there we go. Do you have a feeling for when the prospects for that to move to 5 sigma are? This is using the full available run 2 statistics, right?
Yeah, this is already the full stats. Yeah, so I think we need the run 3 data.
Do you know how much of the run 3 data or not?
If we scale it with the square root of luminosity.
Okay.
Oh, just Yanin, just one more check. I thought you are also supposed to talk about like a multi-boson physics. I mean, you do have a more time.
Yeah, I think I had to be the fastest today. I had a lot of slides, so I only included the interaction of massive gauge bosons, which is profoundly related to the Higgs.
Okay, okay.
So because in my rehearsal, I explained it all the time. So
okay. I mean, okay. Since I thought you're talking sync system. Oh, okay. I mean, since there is time, I can ask you one more question. So, can you look at like your Higgs to the BB for the boosted region, VH? Was it like slide something 12? Oh, yes. Okay, so here I'm a little bit confused. So now if I look at the left bottom, so VH where this V is G boson. So the last data point where PT of G boson is larger than 250. Yeah. So you do have this, I mean, the observed to the standard model prediction is basically, I mean, it's 1. I mean, you do get the signal of the Higgs, right?
yeah, yes.
Now, if I look at the right-hand side, where this, I mean, this is the boosted region, where PT of G boson is, I mean, if you look at dilepton channel, 2L. Yeah, so this is dilepton channel. I assume it's mostly the G boson. The PT larger than 250, here you do not see any signal. It's a, I mean, it's a null. I wonder how, I mean, these 2 data points are consistent. I mean, suddenly I see the, even in inclusive one, the PT of G boson 250 on left-hand side, you do have a signal. But on the right-hand side, I mean, of course, I mean, it's a different analysis, but I wonder how they are, you know, why you don't see in dilepton channel.
Yeah, I think that's a very interesting question. Yeah, first of all, the data are different. So here in the left side, this is a combination of all lepton channels and.
Yes. Okay. So even dielectron, di-muon.
Yeah.
Yes.
And the right side only contains exclusively the boosted analysis.
Yeah. Yes. But my point is the boosted analysis. Here PT of dilepton. I mean, G boson is 250. So if you look, so we only pick up PT of G 250 GB data point. So there should be large overlap.
I think there's also another detail. So the PT here, to the left side is labeled the PTT, and this is the vector boson PT. I think I had the formula to explain this PTT and here, yeah. So this transverse momentum is defined with respect to this so-called T hat direction. So which is the taking this the gamma system. So this is the vector, the x PT vector of the Z boson times the gamma boson, right? So this is direction, not to the z-axis, but the direction of the endpoint of the two vectors. So the PT distribution definition is different in these two plots. That's first of all. Second of all, this is mostly resolved, dominated by resolved analysis. This is a boosted analysis with only 2 leptons. This combines all the number of leptons in this beam. So I think the overlap of the two samples is minimum.
Okay. Let's see. Okay, so thank you, Professor Liu. Okay, so let's move to the third talk. Okay. Okay, so the last talk of this session will be given by Professor Michael Paskin from SLAC and then Stanford University. So he's giving us the talk about precision Higgs physics at future E plus E minus colliders. Let's welcome Professor Paskin.
Okay, there we go. Well, thank you very much. Oh, excuse me. I always forget to do this. Let's try it again. Okay, now we're ready to go. Thank you very much for the opportunity to present at this conference. Actually, it's still, I think, a shame that we can't have PASCOS actually at IBS in Korea. When I accepted the invitation, I was looking forward to visiting Korea again, but hopefully that can happen in the near future. It's always a pleasure to visit that place. Nevertheless, hopefully I can tell you some interesting things about this topic, precision Higgs physics at future E plus E minus colliders. So I'd like to give an introduction that's a little more general than those in the previous talks. I'd like to, first of all, explain why I think the Higgs is so important to study, not only at the level at which its properties seem to be confirmed right now, but at a higher level of detail, and how we hope to get there. And I hope you will see that, in my opinion, the best route to study physics beyond the standard model is really to go after the Higgs boson in much greater detail than it's now understood. So here are the questions I'm going to discuss. First of all, I'm a theorist. Let's talk about some theory. Why is it so important to study the Higgs boson? Secondly, what can we learn by studying the Higgs boson in E plus E minus collisions that we can't already learn from the LHC? Is there synergy between Higgs boson measurements and other tests of the standard model? And I must say, there will always be a word from my sponsor, which is the International Linear Collider. I want to tell you about what this facility is, what its promise is, and describe a little of its physics program. So I think we're all in agreement in one direction or another that the standard model is a very successful theory, but we feel that it is not a final one. There are too many parameters of the standard model that are unexplained, and too much of the structure seems ad hoc. And I must say that of those questions that we have about the Standard Model, some of the most important ones, the reason that this single scalar field appears, the Higgs field, the spectrum of quark and lepton masses, the origin of flavor mixing, the origin of CP violation, they're all not connected to the gauge sector of the Standard Model, which is extremely successful. They're all connected to the Higgs sector. And so somehow there are a lot of mysteries contained in the Higgs part of the Standard Model that we would like to understand. And among these many mysteries, I think there's one which is particularly compelling to me and which I frankly think is the key to all the others. And that is, what is the physics that leads to the phase transition to the breaking of the weak interaction gauge symmetry? Now, we can talk about how this is explained in the Standard Model. The explanation is just manifestly unsatisfactory. What you're supposed to do is to write the most general normalizable potential for the Higgs field phi. You then have two parameters. You assume that one is negative, and then the potential has the correct shape for symmetry breaking. And if you ask why mu is negative, that question cannot be addressed within the model. And actually, it's even worse than that. Because if you try to pursue this question by doing higher order computations within the Standard Model, you get into more and more trouble. For example, the first quantum corrections, the largest two terms are present on this slide. They're both quadratically divergent. They have different signs. And there's no particular reason, although here I put the same cutoff, lambda, for the quadratic divergence, there's no particular reason why those two cutoffs should be the same. Different physics will control the Higgs diagram as opposed to, let's say, the top quark diagram. So not only do we not understand why the parameter mu squared that we observe at the LHC is so small, but we don't even understand fundamentally why it has the sign it does. We can assign it one sign in the fundamental Lagrangian, and that can be completely overwhelmed by these radiative corrections. There's something really missing here, and we need to go after it. Sometimes this is called the gauge hierarchy problem, but I think that's a theorist's way of putting aside what the real question is. The real question is, there's physics here, and we don't understand it. Now, this problem is not particularly new to high-energy physics, because there are many examples of spontaneous symmetry breaking in nature that we actually understand quite well. In condensed matter physics, I'm sure you know many examples, also in nuclear physics and in hadron physics. Probably the most beautiful case of spontaneous symmetry breaking is superconductivity, which is more or less ubiquitous in all metals at very low temperature. For superconductivity, the mystery of why it occurs was really a mystery for a long time. In 1950, Landau and Ginzburg put forward a model that explained many of the properties of superconductors, the thermodynamics of the phase transition, the magnetic properties, the critical current, the existence of type 1 and type 2 superconductors. However, what this model could not do is explain why superconductivity occurred in the first place. So even though this was a fantastically successful model, it didn't answer the most important question. And for this, we needed the more modern Bardeen-Cooper-Schrieffer theory that relates superconductivity to the interactions of electrons in nuclei. And I think this intermediate stage is just exactly where we are in terms of understanding the spontaneous symmetry breaking of the Standard Model. We're still at the Landau-Ginzburg phase. We have a fantastic phenomenological theory, the Standard Model itself, but it doesn't answer the basic question, the most basic question. Now, for superconductivity, physicists knew at least that the explanation had to be given in terms of the interaction of electrons and atoms. For SU2 cross U1, actually, the situation is completely different. We know that the Standard Model doesn't give us an explanation. There are not secret forces there that cause the Higgs to have a spontaneous breaking potential. On general principles, though, the forces must come from some particles and fields. The only thing we know is that we haven't discovered them yet. And I really think that, even thinking about astrophysics, dark matter, the cosmological constant, all those big problems that you guys have been considering this week, I really think this is the biggest opportunity in physics, that there is a new fundamental force which is out there at short distances, which gives us the physics of electroweak symmetry breaking that we don't know about now and that we have the opportunity to discover. Okay, now, it is true that since the discovery of the Higgs boson in 2012, many of its couplings have been measured by LHC experiments, and frankly, in fantastic agreement with the Standard Model. And I think that Professor Liu showed you this plot in his talk and a comparable one from CMS. If you test the linearity of the relation between the fermion masses, and actually also you can put on the same plot the vector boson masses, the masses that are supposed to be generated by the Higgs boson, and then if you compare that to the couplings which are measured for the Higgs boson, these line up in a very fantastic way. And the errors are shown on the bottom. We're talking about agreement at the level of 10 to 20%, but still remarkable over many orders of magnitude. So a lot of people ask, well, isn't this enough? The Standard Model agrees with experiment, no matter where it comes from. Let's just be happy and try to go on as best we can. And I think that this is really not the right attitude, because despite this fantastic agreement that's come from a lot of hard work from the LHC experiments, we still actually know very little about the Higgs boson. We know that it's the agent of electroweak symmetry breaking. It is the source of the order parameter, if you like, for this phase transition. But there are a lot of things we don't know about the Higgs boson. We don't know whether it's fundamental or composite. We don't know whether there's only one or maybe more Higgs fields. We don't know whether there's a whole new sector of additional particles related to the Higgs. And there are all kinds of theories out there that really make the Higgs into a much larger deal. For example, supersymmetry, the idea that Higgs might be composite, the possibility of extra dimensions. All of those theories have the possibility of explaining electroweak symmetry breaking. But the price is an enormous increase in the number of fundamental particles. And they could be out there, we just have to discover them. So I think it's an important question to discuss. How can we have so much knowledge and so much ignorance at the same time? And there's an explanation which is ready to hand that comes from effective field theory. So the reason, we would say, follows from the fact that whatever these new particles are, they haven't yet been discovered at the LHC. As long as all this complication is there in nature, but the masses of the particles are large, not so large enough to be at a TeV scale or otherwise out of reach of the current LHC experiments, you can form an effective field theory in which they're integrated out. Within this effective field theory, the only source of electroweak symmetry breaking is the Higgs expectation value. And also the couplings, the effective couplings of the Higgs, are supposed to be very close to their Standard Model values. So one way of thinking about it is that the masses of Standard Model particles reflect the Higgs couplings at q squared equals 0. The Higgs partial widths and the couplings reflect the couplings on the Higgs mass shell. Those two q squareds are maybe separated from one another, but they're very different in terms of the contribution from heavy particles. And so the relative contribution from heavy particles is small, of order mh squared over m squared. If m is of order of TeV, we're talking about percent level corrections to the properties of the Higgs boson with respect to the Standard Model predictions. And that really comes only from the fact that the particles involved here are heavier than maybe we thought they should have been. And by the way, this estimate can be proved as a theorem in Standard Model effective theory. It's called, in that context, the Haber decoupling theorem. Now, how do we know that these new particles are heavy? Well, they could actually be light. There are some exceptions, but roughly, we've not discovered them at the LHC. Why are they so heavy? I think this is an interesting problem. It's one that I've actually been working on recently. I think a lot of other people have given attention to it. It's a different problem from what's usually called the hierarchy problem. It's called the little hierarchy problem. Why is it that the things that cause the electroweak symmetry breaking are not at 100 GeV, but they're rather more like a TeV? I think that problem is likely to have an interesting explanation, and probably one that's very important to this whole picture, and it really deserves our attention. But the point I'm going to make in this lecture is that it's quite consistent with everything we know that these effects are at the 5% level or thereabouts in Higgs couplings, and that experimentally we can actually reach that level and learn things about new physics by doing precise measurements of the Higgs boson couplings. So this is true for two reasons. First of all, the 125 GeV Higgs boson has a very large number of possible decay modes. There are actually 10 decay modes. I've listed 9 of them here, with branching ratios in the standard model above 10 to the minus 4. And so by systematically going through and checking each of those couplings, one can gain an enormous amount of information. Secondly, within the standard model, the partial widths to each of these modes are completely computable, since the standard model is now totally defined after we have measured the Higgs mass. That basically gives us the last fundamental parameter. So we can make predictions of very high accuracy. And if we can do experiments of very high accuracy, we can look for these small deviations. Now, actually, the story is more interesting than that, because the Higgs couplings are small, but actually they're all different. Each Higgs coupling, in some sense, has its own personality and is guided by different types of new physics. And very roughly, the classification of those, this is a very rough statement, but it's verified by looking at many specific models of what can be beyond the standard model. The fermion couplings can be modified if you have 2 or more Higgs doublets. The gate boson couplings are modified, actually, typically, they're not modified in supersymmetry, but they're modified in other kinds of models where you have mixing with Higgs singlets or where the Higgs bosons are composite. For example, Higgs has a Goldstone boson of some new composite sector. The gamma-gamma and glue-glue couplings come from loops. And so in addition to the usual things that appear in those loops in the standard model, top and W, heavy vector-like particles can appear in those loops. The top coupling, of course, has its own special role. In models where the Higgs is composite, the top is also composite or technically partially composite. And that can have an effect on this particular couplings. And in the triple Higgs coupling, there's actually the possibility of large deviations, which, as was discussed earlier this week, are actually needed if you have a model of baryogenesis at the electroweak scale. So what we'd like to do is to go a level deeper than the LHC experiments have been able to do, to really look for these small deviations, to understand their pattern, and to try and deduce from that pattern what the physics is beyond the standard model. Let me just show you a couple examples. This is from a paper by Wells and Zhang. What you see is a map in some parameter space that I think I'm not going to explain, of the deviation in the Higgs coupling to BB bar. So between 10 and 5 is the yellow band, between 5 and 2% is the green band. As you see, there's a lot of phase space for such small values, not much phase space for the very large values that one might have hoped for. That's a consequence, again, of Haber's decoupling. The solid line shows the current exclusion in this plane by direct searches, and the dotted line shows the expected exclusion from high luminosity LHC. It would be nice if high luminosity LHC were to find a point corresponding to something in that band, but even if they're not able to, you can see there's a lot of phase space beyond that, which is accessed by looking for the coupling in the Higgs coupling. And so in general, this is a general phenomenon that models of new physics predict a new particle mass spectrum. Some of the particles might be light enough to be observed directly at the LHC, but they also produce corrections to the Higgs couplings. And once you reach this level of precision, those are two really different routes to discovery, which are complementary to each other, and which really might rely on these precision measurements to break through to new physics beyond the standard model. Here's another of these parameter spaces by the Liang and his collaborators. Here, what's plotted are some models that involve real scalars mixing with the Higgs boson. In the vertical axis, what you see is the modification of the Higgs-ZZ coupling. Actually, the current limits are really just at the top. The top red points are excluded now by the best LHC measurements. What goes along the horizontal axis is the triple Higgs coupling. And you see that these models can produce quite large deviations in the triple Higgs couplings. Still, I must say, really out of reach of the LHC, but we'll see that one can actually explore this whole plane with E plus E minus experiments. Actually, in the paper that's referred to at the bottom of this slide, a group of us tried to collect a set of models with relatively large deviations, typically in only one or two Higgs couplings, and compare them. And what you see from this slide is very clearly, as you go from one of these models to another, maybe I should say these are not generic models of the parameter space. They're specific points, but nevertheless, they are points that represent things that could be out there. As you go from one of these models to another, the pattern changes. If you have the kind of accuracy that you see with the pink triangles, with the pink rectangles, you can actually distinguish these models, and you can learn what kind of physics is out there beyond the standard model, hopefully the physics that now explains electroweak symmetry breaking and many other phenomena. So this is really what we want to go for. Can we make measurements accurately enough to produce those tiny pink bands on this plot and really learn something about new physics from this point of view? So now I'd like to turn to the special advantages of studying the Higgs boson in E plus E minus annihilation. So these go beyond the usual advantages for any high energy physics measurement, that E plus E minus gives you very low backgrounds, the ability to reconstruct the full event, the access to W and Z in their hadronic decay modes, which is often important to get the whole picture of what's going on, and allowing the use of beam polarization, which is a very important handle, especially for the weak interactions, which are parity violated. Let me go on a step further by showing you the important processes that produce the Higgs boson at E plus E minus colliders. As you go up in energy, the first one you encounter is the Higgs-Strelung process. E plus E minus annihilating to a virtual Z, producing a Higgs boson recoiling against a real Z. This is actually a fantastic reaction, which I'll talk a little more about later. But what it says is that every Higgs is tagged with a Z boson, allowing a very model-independent and background-free method for studying the Higgs. At higher energies, vector boson fusion also becomes a very important production mechanism. You can also, at still higher energies, produce the Higgs in association with top to measure the top quark Yukawa coupling, and measure Higgs pair production, as you can at the LHC, to measure the triple Higgs coupling. Here's a map of the cross sections, at least for the Higgs-Strelung and WW fusion. And you can see that if you have an E plus E minus collider with an adjustable center of mass energy, as you do at E plus E minus, the center of mass energy is very well defined and it's at your control. You can move from one regime to another, starting, for example, at 250 GeV in the center of mass, where you're at the peak of the Higgs-Strelung cross-section. And as you go up, getting more and more statistics from the WW fusion process, the two reactions being complementary, and also, because we're talking about precision measurements, verifying the systematic errors that you would assign to each of the others. Here's an example of what you can learn from directly from this tagged Higgs measurement. Remember, at 250 GeV, where the simulation occurred, basically every Z boson with a lab energy of 110 GeV recoils against a Higgs boson. So if you look at that signal, there's a background that comes from E plus E minus the ZZ. This is well understood. It can be computed at the 10th percent level, so we really know very well how to subtract it. There's a very narrow peak in the recoil mass that corresponds to the Z, to the Higgs rather. If you fit that out, the error in the Higgs mass is 15 MeV from this analysis. So we're talking about now knowing the Higgs mass to 10 to the minus 4 accuracy by not observing the Higgs itself, but by observing something that tags the Higgs in recoil. By the way, to interpret the Higgs to WW and Higgs to ZZ couplings, you actually have to know the Higgs mass to that accuracy. So it's good to know that you can do it. Let me just slide you through some other simulation results. Here's what Higgs to tau tau and Higgs to BB bar events recoiling against a Z are supposed to look like in simulation. There are very complicated ways to find taus in hadron colliders, but at E plus E minus colliders, a tau pair is a 1-prong recoiling against a 3-prong. And you see that that's kind of obvious in the simulation. Similarly, in BB bar, we're looking not only, if you look at the inset, in the primary B vertex, but also the secondary charm vertex, which gives a very powerful tagging handle, 1B, and actually you can tag charm as well. Here's what the observed mass distribution looks like in W fusion. In W fusion, neutrinos go away. The Higgs is the only thing in the detector. You can see the very clean separation between W fusion to Higgs and to Z. Here is an analysis done by the ILD group interested in ILC, which shows the ability of an appropriately defined neural network to separate the various hadronic modes. So one can very cleanly separate Higgs to BB bar, Higgs to CC bar, and Higgs to glue glue and measure them separately, as we'll see, beyond the percent level of accuracy. Now, there's one small thing that we have to discuss. I'll try and, I guess my time is okay, but I'll try and be brief about this. I've already told you that the measurement of Higgs branching ratios is very straightforward for the ILC or for any other E plus E minus Higgs factory at 250 GeV. You just sit in the center of mass, you look for Z bosons coming out at the lab energy of 110 GeV. Whatever is on the other side is a Higgs boson. And then you just count the different kinds of final states. All Higgs decay modes are visible, standard model, exotic, even an invisible Higgs decay. You see that Z and nothing else, so you know the Higgs decayed invisibly. The measurement accuracies are such that 1% coupling measurements are feasible. Because you're counting Z's, the absolute cross-section can be measured. And that'll be very important in providing not only the relative couplings, but the absolute scale of Higgs boson couplings. Now, though we can measure the branching ratios, there's a potential problem in converting these to absolute couplings. The width of the Higgs boson is very narrow. It's predicted to be 4 MeV in the standard model, and this would not be directly measurable at any proposed collider. However, in E plus E minus colliders, there is, well, let's just start with this, an apparently model-dependent way to determine the Higgs width. You measure the branching ratio of Higgs to ZZ. You measure the cross-section, which, as I said, can be determined absolutely. The branching ratio is the ratio of a partial width with the total Higgs width. Both sigma, both the cross-section and that partial width, naively at least, depend on the Higgs-ZZ coupling, so it cancels out and you get the partial width. It's not an optimal method because the branching ratio that goes in the denominator is quite small. It's about 3%. So you lose a factor of 30 in statistics. But at least it gives you the idea that with some better idea, you could really use the full set of Higgs data to measure the Higgs width, maybe a little indirectly, but nevertheless in a very model-independent way, very accurately. Actually, we've discussed that you can improve this situation by the systematic use of standard model effective field theory. Given that the corrections in Higgs physics to the standard model are very small, we can parameterize them as corrections to the standard model from operators of the leading non-trivial dimension, dimension 6. So you have a set of dimension 6 operators that you add to the standard model, which gives you an almost model-independent parameterization of new physics. You then try and fit those parameters from the corpus of Higgs data, and I'll tell you later from other data that you can obtain in an E plus E minus collider. And then given that, you can determine the deviations from Higgs couplings that are determined by those operators. Now, it turns out that the description in this way of the deviations in the Higgs boson couplings to B, C, tau, and GLU are very straightforward. They're each controlled by a single coefficient in the dimension 6 Lagrangian. For W and Z, actually, there are two independent structures that arise from dimension 6 operators. The first one, as you see in this equation, having the usual form of the coupling in the standard model. The second one, parameterized by this parameter zeta, has to do with the Higgs coupling to the field strengths of W and Z. So actually, the argument I gave you a couple slides ago was wrong. Dividing the cross-section by the branching ratio is not model independent, because you only eliminate one combination of these two parameters. You have to actually do a little better, including more information. But fortunately, the standard model effective field theory gives you a solution to that, because it gives relations among these parameters that are non-trivial but tractable. The two eta parameters, it turns out, are related by the quantity CT, which also leads to the T parameter of precision electroweak. And that's known to be very small. So they're basically equal. For the two zeta parameters, there are some non-trivial effects, but that parameter, for example, CWB, can be determined by measurements of E plus E minus to W pairs. And CBB is related to the Higgs branching ratio to photon-photon, which can be also directly measured. And also it turns out that this parameter zeta Z or zeta W is very sensitive to the polarization asymmetry in E plus E minus to ZH. So this is a way to use beam polarization to really get some extra information about the Higgs properties. So we're going to try and use all of these available techniques to use the direct measurement, the measurement of branching ratios, the beam polarization, the absolute measurement of the Higgs-Strömlin cross-section, and the measurement of other electroweak processes, E plus E minus to W pairs and E plus E minus, and maybe I should say ordinary precision electroweak, to get a single coherent picture in the standard model effective field theory, which in turn will lead to very accurate determinations of the individual Higgs couplings. Now, there are a number of proposals for E plus E minus Higgs factors around the world, CPC in China and FCC at CERN, which are large 100-kilometer circular colliders, CLIC at CERN, which is a linear collider, and ILC in Japan, which is a linear collider. All four of these projects have very similar physics programs, and when you work through their expected reach in terms of the accuracy of Higgs couplings, those are also very similar. I think right now the ILC is probably the one that is most on track to actually be constructed. And so I'll explain that at the end of the talk, but for the moment, I'm just going to show you some slides that have to do with the plans and projections for ILC in Japan. So the basic idea is shown at the bottom of this slide. You have two linear accelerators producing electrons and positron beams that interact at an interaction point. You build a fancy detector at that point. Actually, to do these measurements, you need a detector that exceeds by some large factors the capabilities of the LHC experiments, using the fact that the E plus E minus environment is much cleaner and lower background. You can do that. And then in that environment, you're going to make these measurements. Here is the ILC candidate site in Kitakami in the Tohoku region of Japan. It turns out that you can find a place in Japan that is basically sitting on a single piece of granite without earthquake faults running through it. And that's very advantageous for this purpose. So the simulations have been done. This really can achieve very high levels of precision in the beam dynamics. Here is the proposed run plan. As you see, beginning at 250 GeV, there's a technique for a luminosity upgrade. Then you would essentially make the accelerator longer by adding longer pieces of the LINAC to make an energy upgrade to 500 GeV. The first thing is, as you see here, a 22-year program comparable to the length of the LHC program. By the end of it, you have made a lot of progress, and let me just try and illustrate that now. Here are the expected total integrated luminosities at each stage, and in all the stages, you'll have its expected E plus and E minus beam polarization, 80% polarization for the E minus, but also a very useful 30% polarization for the E plus. And so if you now take those numbers, take the standard model effective field theory analysis, put it into a big pot and stir, this is what comes out. So what's shown here are the accuracies to be expected in the individual Higgs couplings in percent at various stages of the ILC program. So the green is the expectation for the 250 GeV stage. The blue is the expectation value for a 500 GeV stage. There also can be tacked onto the end a 1 TeV stage, and that stage maybe is not so interesting for looking at the actual Higgs decay modes, Z, W, B, tau, G, C, but it's very interesting for some of the other couplings of the Higgs that you might be interested in. We're talking about a, I think 1.6% measurement of the Higgs top quark Yukawa coupling and a 10% measurement of the Higgs self-coupling if you can get this machine to operate at 1 TeV. Here's a comparison of HLLHC and ILC projections. So here I have just the 250 and the 500 stages of ILC, as you see on the previous slide. There's a difference from the previous slide because HLLHC, the projections are always model dependent. They have model dependent assumptions. And so here we've used the same model dependent assumptions to analyze the ILC data just to make a fair comparison. And as you see, it really is a dramatic qualitative improvement over what people think is possible at even the high luminosity LHC. As I've emphasized before, this improvement is really necessary to get us into the game of precision Higgs couplings. If there's a 3% deviation, you'd like to measure that at 5 sigma, which means your measurement accuracy had better be below 1%, and you should have a strategy to get there. At the energies above 250 GeV, there are lots of other things to do. There's a precision program in the top quark, the reactions E plus E minus to FF bar probe for new vector resonances, and for very high compositeness scales. And I don't have time to talk about those things here, but if you look in the reference that I've quoted here, you'll find the projections for all of those studies. Here's just what the top quark threshold looks like when you measure it in E plus E minus. You can see that there's a lot of detail that can be extracted. So that too is going to produce a very large increase in our knowledge of this other mysterious particle of the standard model. So I'm almost done, but in the last part of the talk, I'd like to say a little about the timeline for funding and construction of the ILC. Personally, I'm very optimistic about this now. The ILC has been around for a long time. Its status has gone up and down with various political and physics currents, but I think it's up now. And there's a reason for that, which I think is fairly clear. The LHC has done beautiful work, but we're now seeing the limits of the LHC program. We're seeing more and more how the systematic errors, which are inherent in hadron collider physics, are providing limitations. we see from what I've just told you the necessity of going beyond that to a very high level of accuracy. And this is something that we know how to do. We know how to build the accelerator. We know what we need from the detector. We know how to improve the theory also to allow these measurements to make precision comparisons with the standard model. It's really time now to do one of these Higgs factory programs. The ILC is an expensive project with a cost comparable to the LHC. I think there is national interest in Japan in hosting the ILC. I showed you the chosen site. Of course, Japan can't do this alone. We have to somehow come to an agreement, or global agreement, similar to that funded the LHC, to provide support for Japan in hosting this project. And so last summer, the ILC International Development Team was set up. And the purpose of this team was to design and carry out the first stages of a gradual process toward the required international collaboration. The chair of this team is Tatsuya Nakata, who was actually the chair of the 2013 European Strategy Study. And so he has taken the lead in trying to outline a program toward the realization of the ILC. And here's a slide that he gave at the October 2020 Americas Workshop. So the rough timeline would be something like this. The IDT will prepare the scenario. That will then go to an ILC pre-laboratory, which will be located at KEK. And that will now make the site-specific technical design. So at the end of that process, you're really ready to bring in bulldozers and dynamite and start constructing the tunnel and the accelerator. It will prepare scenarios for regional contributions, and it will give a period for the governments to come together and quarrel about who's going to spend how many $1 billion to make this actually realized. Once that process ends, we can then begin construction of the ILC laboratory. So thinking about that as a 4-year process, the ILC laboratory would begin in 2026 and have its first data in 2037. So it's interesting, the ILC can run contemporaneously with the last stages of the LHC, a coincidence that brings some interesting advantages. And I think if you're 20 today, you'll be 40 in 2037. You'll be at the peak of your career, and this is going to be the opportunity that you want to really advance our knowledge of fundamental physics. So let's hope we can keep on this schedule. So far, so good. The first thing the pre-lab was supposed to do was to make a proposal. Sorry, the first thing the IDT was supposed to do was to make a proposal for the ILC pre-lab, and that's now appeared on the archive. So that's also will be the basis of a specific funding proposal that will be submitted by KEK this summer. And we, let me just say, anticipate, hope for, I'm not sure is the right word, the approval of that in next year's Japanese budget. ICFA, the European Strategy Report, and the US DOE and State Departments have explicitly encouraged this process. And in the lead up to the ILC pre-lab, there is now a new physics and detector organization under the IDT. Hopefully this will continue when the pre-lab is funded. There's a reference, as you see the URL here. If you're interested in getting involved in that, send me email, and I'll try to get you connected with the people who you might be interested in working with. So that's what I wanted to tell you. I think we're now on a path to learn from experiment about the nature of the Higgs boson and the mechanism of electroweak symmetry breaking, and hopefully to learn about all the other mysteries of the standard model that come from the Higgs sector and require its understanding. The experiments, I believe, have a good prospect to discover a new force of nature that plays an essential role in fundamental physics. So I strongly encourage you to learn more about this program and to join in. So thank you very much.
Okay, so thank you for your very interesting talk. So we can take a few questions. So you can raise hand or you can directly ask question to Professor Baskin.
Yeah, I don't have the chat while I'm sharing, so you have to tell me what the question is.
So, Michael, I'll ask a question. This is Todd Adams. So, thank you for your wonderful talk. You always challenge my assumptions on what I should be doing for physics when I hear you speak. I think maybe I should be running off and changing my direction. But one of the things that surprises me when I look at an E plus E minus when we talk about a Higgs factory is how few Higgs bosons are actually produced. So my question was, you showed measuring the Higgs mass to 15 MeV, I believe you said?
Yes, that's right.
How much data is that to accomplish that?
Okay, so the whole sample at 250 GeV, according to the schedule that I showed you, is 500,000 Z bosons. So 500,000 Higgs bosons. Each Higgs boson is tagged by a Z, but the Z's are not all equal in terms of making that measurement. You really want the Z to mu plus mu minus decay to have the smallest systematics in that measurement. So we're talking about 3% of 500,000, so 60,000. It's still a lot of Higgs bosons, considering that everything's precious, that the backgrounds are really very small.
Okay, the peak you showed was in the hundreds of events tall. I didn't know how many years of running that was accounting for.
This is, oh, you're right. I'm actually not sure. There's some efficiency because you have to select the best mu plus mu minus pairs. I'm actually not sure how much data is in this simulation.
Okay.
But the full sample that you're talking about is 500,000 times 3%. And so then, of course, there are efficiencies and cuts that would make the most golden measurement.
All right, thank you.
I think if you look at the reference that it's at the bottom, all the details are there. Actually, that's a long paper, but there is a specific discussion of this reaction.
Do we have any other question? Okay, so otherwise, last thanks to Professor Paskin again. And then also I like thanks to all of the speakers in this session. I mean, it was all very interesting talk. And then with this, I like to close this session.
Let me say, we thank the very beautiful organization of this conference.
Thank you too.
Appreciate it.
Agreed.
Okay, so next session will be after 20 minutes in 2 parallel sessions. Enjoy your symposium. Thank you.
Very good. Thank you.
Bye.
Bye.